Does anybody have any homework questions? Okay, then let's take a look at 7.2. 7.2 won't be due until next Sunday night. We were looking at fractals. One of the fractal-like areas we have is the coastlands. Yeah. Oh, thanks. Yeah, thank you. So we were looking at fractals, and one of the fractal-like areas we see are the coastlines. Because if you zoom in on a coastline, it looks the same. It has the same sense of self-similarity. And you zoom in and you zoom in, and if you can picture yourself standing by a coastline, you would see a lot of zigzagging going on, just like we see when we're further out from a coastline. So remember, a fractal has a sense of self-similarity at different scales. They can be infinitely detailed when they're manufactured by people. I wanted to show you some landscapes here. Here we go. Okay, 2 images. I wanted to show you side by side so you could tell which are which. So I guess I will go to the document camera. I thought they might look a little better on this computer screen, but no. So we have 2 images. One is computer generated, one is a photograph. In each case, one is a fractal and one's a photograph, and I'd like you to guess which is which. Okay, so you have the moon on the water. One of the applications of fractals is for creating scenes in movies, that you can just get a real-like image. And sometimes an image that doesn't exactly exist in nature, but it looks like it does. Let me see if I turn the light off if there's less glare. Yeah, that's a little better. Okay, so guess which one is real, which one is a photo. Here's some more. Okay, here's another set of 2. One of these is real, one is a photo. Next one is real, one is a photo. No, yeah, the real one is a photo. One is a fractal, one is a photo. And one more set. So we had 4 sets. One is a fractal, one is a photo. Okay, who thinks the left one is the fractal? Who thinks the right one is the fractal? Okay, yeah, the right one is the fractal. Okay, back to the moons. Who thinks the left one's the fractal? Who thinks the right one's the fractal? In this case, the right one is also the fractal. So the left one is a photo. Okay, what do you think? Is the right one the fractal? Who thinks the right one's the fractal? Okay, and who thinks the left one's the fractal? Okay, it was the right one. The right one's the fractal here. And 2 more. Who thinks the right one is the fractal? Who thinks the left one is the fractal? It's actually the right one that's the fractal. So fractals can be used in making movies. We're not going to make fractals that way. We're going to look at different uses. There are different applications too for fractals, and the kind that we're making this morning will be more along the lines of an application where you use it for, here, I'll show you. So here's the application of a fractal. You can see it's how tree-like it is in its nature. That fractal is used to distribute heat on a circuit. So it's a fractal-like image to distribute heat. The types of fractals we'll make will be more along those lines this morning. Here's some fractals that are used instead of stirring. These are to distribute fluids within fluids instead of stirring. So these are 3D fractals so that you don't stir and disrupt and get random placement of your chemicals, but instead have a very precise and yet fractal-like way of placing chemicals. So our question the author starts with is, how do you turn a triangle into a snowflake? And we're going to explore ideas by carrying them to the extreme, and that will give us an idea of how fractals can be made. So we'll look at a couple different ways fractals can be made. First off, if you have a straight edge, that's what you'll need, okay? And then you'll need a lined piece of paper. We're going to need a fairly big piece of paper. If you don't have a straight edge, your ID can serve as a straight edge. But it would be nicer if you had a straight edge, because then it would be a little more precise. Because I'm going to ask you to make line segments of a particular length. I wonder if it would be better if you don't have a, you know what, if you don't have a straight edge, if you took another piece of paper so you could kind of use it like a ruler, like you could make, 4 lines long or 2 lines long, so you could kind of use your paper like a ruler. So you will want pretty careful measurements. So one way to make a fractal is to just keep replacing a part with itself. So we'll start with that. I'm going to make a fractal 9 inches long, so some multiple of 3. If you're using maybe a 3x5 card to be your straight edge, you could choose some multiple of 3 that will make that handy. And what we'll do is we'll draw 3 inches, or 1/3, whatever you have. 3 inches, then leave blank 3 inches, and then 3 inches more. And if you have a compass, this is even better. So hopefully you still have your compass in your bag. Because now what we're going to do is we're going to take those same 3-inch line segments and make a peak in the middle. So the way to make a equilateral triangle is to take your compass and put one point on one corner and drag the compass arc, and then put the other point on the other corner. Your arc doesn't have to be a particular size. I just made it almost the full size. So if you have a compass, then you can get a perfect 3-inch length here. If you don't have a compass, you're going to have to try and take whatever length you use here and draw it here. Okay? So this is something I would ask you to do on a quiz. So you'll want a straight edge and a compass on your quiz again for quiz 3. And this is something you can practice with Jake in study group if you go to study group too. Okay, so this is going to be our first stage, our first iteration. So sometimes we call these stage 0 and sometimes we call them stage 1. I'll just call it stage 1. Now what we're going to do is we're going to shrink this down 1/3 as long as it is. So this is presently 9 inches. I'm going to shrink it down to 3 inches. And once I've shrunk it down, I'm going to put a copy of it here, 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 and here. So I'm going to make 4 copies of this, each 3 inches long, and put them where the line segments are. So now when I sketch up here, I was using 3 inches. However long you were using, you want to break that up into thirds. So take your line segment that's down here and break it up into thirds. So, oops, and then, yeah, that's what we're going to do, okay? And then we're shrinking this whole piece down to be a third as big as it was, as third as long as it was. So now I'll take and make a peak here, an equilateral triangle. So for me, these are each a 1-inch unit now. That didn't quite come out to an inch. I wonder why. Let me try that again. You know what, now that I think about it, you should have your compass be this long, 1 inch long when you want to make a 1 inch peak. I wasn't thinking before. Okay, so we got a 1 inch peak there. Okay, so we've shrunk this down, this stage 1 down to 1/3 as long, and then we've placed it on this line segment. And now we do that again for the other 4 line segments. So we take that, make 4 copies of this and put it on these other 4 line segments. So I'll make the copy way to the right next. So that was between 6 and 9 inches. And you can see why they invented computers to do this, right? It's a little bit fussy. But I think by doing it yourself, you get a feel for how fractals can be formed by taking and making smaller copies of itself and placing them in the line segments that were originally there. Okay, so we have the 2 ends shrunk down, and now we're going to take these 2 line segments in the middle here. So I better get them positioned correctly. So I'll find the peak again. So I want the point, only instead of drawing the point made out of just 2 line segments, I'm drawing this shape, this shrunk down stage 1. And while I have my ruler out, I think I'll do the other side as well before I get my compass out. So a fractal has a sense of self-similarity across different scales, and we're seeing here that that we have this portion is similar to the whole thing in some sense. As we keep going, it'll get more similar. So this was stage 2. Okay, so let's see how you're doing. Does anybody have any questions? Okay, well, we're going to do that again. We're going to take this stage 1 and shrink it down and put 1 on each of the line segments. So how many copies of stage 1 do I need to place on here now? How many line segments am I going to be filling up with stage 1?
16.
Is it 16? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Good job. 16 it is. So 16 copies. We're getting kind of shrunk down here, so we're going to be real little now. All of our line segments are just going to be about 1 inch. And I think I'm going to have to drop it down and have the peak inside a bit because I think it'll be too tall otherwise. So this time, just have 1/3 of an inch and 1/3 of an inch, and then I'm going to have a little peak. And then my little peak in there with its 1/3 of an inch is going on. 1/3 of an inch and 1/3 of an inch. And down here, same thing. 1/3 of an inch and 1/3 of an inch with a little peak. Another 1/3 of an inch and 1/3 of an inch with a little peak in there. Let's just kind of freehand the peaks this time, huh? It'll be a little less precise. But I think I'll still be a little precise for these peaks. So we're making 16 tiny copies of stage 1 and putting them on all 16 line segments. Yes?
How far are you going from like the baseline of stage 1 to the baseline of stage 2 to the next one?
You mean the actual inches measurement?
Just like, is there a specific amount, or?
I guess I'm not sure what you're asking. So stage 1, I use 3 inches for each line segment.
Yeah, so from like the top of the
Oh,
stage
from
1 triangle,
up to here?
how far up to the baseline of stage 2?
Right here?
Yeah, do you go?
Oh, like this distance then?
Yeah.
That's up to you. That's extraneous. This one I made lower because I didn't think I had room on my paper.
Okay.
And I figured it'd just kind of be inside like a hat on top of a hat. Okay. Any other questions? Okay, so this time the 1-inch segments have 1/3 and 1/3, and then 1/3 and a 1/3 making a point. One-third and a 1/3 and a 1/3 making a, oh, that's a terrible one. Okay. All right. Okay, do this one. So a 1/3 and a 1/3. So each one of these makes, there's 4 basic line segments, and then they have a point in them, and we're putting one of those 4 basic line segments into each of these original line segments. Hopefully I didn't go off my page. Nope, just made it. Okay. So really what we're doing is we're putting a stage 2 4 times. Okay, we shrunk stage 2 down and we're putting it down 4 times. 1, 2, and now I need 3, 4. So stage 2 shrunk down 1/3 as long as it was. So 1/3 of an inch. So none of your line segments should be more than 1/3 of an inch now, or 1/9 of whatever you started with. So we're seeing a sense of self-similarity in that at different scales we have the same figure. So we have this stage 0 shrunk down and showing up on each of the stage 1 shrunk down and showing up on each of the line segments in stage 3. We have stage 2 shrunk down and showing up on each of the line segments as well. Now, fractals have infinite complexity, so we could keep doing this and keep doing it, right? I'll come around and see how yours came out. Online students, feel free to email me your pictures and see how they're coming out. Okay. And just stop me if yours isn't coming out. You shrunk that down, put it here and here, and now put a point here, and then put this copy going up to the point, and up to the point. So you're taking this and putting it here and here, basically. Okay. I want you fast. See that? Oh, this is great. Oh, this makes it also nice. Yeah. Point, main point. Yours is off the paper too, isn't it? Is that like a screenshot? Yeah. Oh, that's nice. Looks like
I started too small, so it wasn't possible to
oh, that's okay. You're doing it. Yeah, yeah. I can see that because you put the students there and there. So that's exactly what we need to do. I don't know if I saw everybody's. Is anybody stuck? So we're just shrinking this original stage 1 down, and first we put it on the 4 line segments of stage 1, and that made 16 line segments. So then we shrunk it down to go on each of those 16 line segments. So on a test, I would just usually ask for the first 2 stages because it takes so much, or else I would ask you to cheat, because if I asked you to do stage 3, you could use another color. So that's a little easier, right? If you take another color to stage 2 and just trace right next to it, just go like this. So that would be a way to do stage 3 on an exam, just on a quiz. Just go ahead and make it right piggybacked on top with a different color, and then identify that color. Okay. So one way to make a fractal is to just shrink down the shape and replace each shape with the shrunk down version. And you can continue doing that forever. And we have on Wikipedia a computer simulation doing that, just shrinking it down forever. So I'll go ahead to that screen and show you that, okay? So here's the this is called the Koch curve. We'll label that in a minute. This time the Koch curve is done 3 times and then connected into this triangle. And you can see if you make it in 3 like that, you get a snowflake effect. So this simulation has 7 iterations going on Wikipedia. And below you see the infinite detail. So let me get a fully drawn Koch curve from my notes to show you.
So is this the Dropbox then?
It is, yeah, the Dropbox. Yep, very good. Okay, so let's label this Koch curve. And 7.2. Okay, that's the section we're on, 7.2, Koch curve. So when you're looking through your notes, you know what you're doing. And that goes in the Dropbox for Sunday night. And the 7.2 Wiley Plus material isn't due until the following Sunday, so that you can ask questions next Monday. And plus, we might not be done. So here's a number of iterations. This picture is in your book. We stopped right here. And can you see how you could circle part of the curve and it looks like the whole curve? So that's one of the things I'll be asking you to do as well. Can you think about what part of this curve you could circle and it would look like the whole curve? So there's a couple of places. One would just be to take one of these pieces, one of the 1/4. Okay, so you put this together 4 times to make the whole thing. Or if you didn't see this, if I covered up this part, what you have left looks like the whole curve only shrunk down. Okay, so there's that sense of self-similarity on a different scale. Now, can anybody see a smaller version of this that you could circle as being similar to the whole thing? Okay, so you could also pick this little tiny piece right here. So that piece looks like the whole curve on a smaller scale as well. So we have this sense of self-similarity on different scales. Let's try another shape. Let's make the Sierpinski triangle. So the Sierpinski triangle, you'll be happy to know, is simpler to draw. So the Sierpinski triangle starts with a equilateral triangle. That means all the sides are the same length. So I'm going to make an even length. I'll pick 2 inches. And since I have a compass, I'm going to use the compass to make the other sides 2 inches as well. But if you don't have a compass, do the best you can to make all the sides the same length.
How long is the bottom?
I made mine 2 inches. So we start with the equilateral triangle, and that's stage 1, or again, some systems use stage 0 to start. That's why it's easier to say the first iteration instead of what stage you're at, okay? So stage 2, we take 3 of these and build them together. So now we're going to make 3 equilateral triangles whose sides are half as long as they were. So I'll say 1 inch long. So I'm going to make 3 equilateral triangles and stack them together. So here's my 1 inch mark. So I'm going to mark off the 1 inch mark as I draw this. So 1 inch right here. So these 3 equilateral triangles stacked up now are each an inch on each side. This one is empty. The upside down triangle is empty. Okay, so these 3 triangles are stacked up. They're the same as what I started with, only smaller. So what we'll do now is shrink stage 2 down and put it in each of those 3 triangles. So the empty upside down triangle stays empty and upside down, but now we shrink stage 2 down and we put it in each of these 3 triangles. So now my triangles are only going to be a ½ inch long, or a 1/4 of whatever you were doing before. So as I measure, I'm going to mark off the ½ inches because I'll need those. So I had these triangles that were 1 inch on each side, and now I'm going to shrink down this stage 2 and fill it into those triangles. So when I shrink down stage 2, I get, how many triangles will I have? If you just count the right side up ones, how many would there be?
3.
So there were 3 right side up, and then in stage 3, how many right side up will there be? 9, yeah, one set of 3 in each. So now I have 1, 2, 3, shrunk down, and I'll do the same thing over here. So this triangle, this Sierpinski triangle, is easier to sketch. So on a quiz, I would ask you to sketch 3 stages because it is easier to sketch. Or even 4, because then we can kind of cheat like we did on this version of the Koch curve where we just drew over top. Because we could draw over top of stage 3 with another color to make stage 4. So we thought of this, and I described it as taking smaller images of stage 1 and then smaller images of stage 2 and putting them together. But you could also think of it as removing the center. Okay, so you could think of this as removing the centerpiece and then removing the center of each of these. So if you thought of that, you could make stage 4 in another color just by removing the center with an upside down triangle of all the right side up triangles. Okay, so you ignore the upside down triangles and add your own upside down triangles, and that gives you stage 4. And that's pretty simple to draw if you don't worry about using your straight edge. So the upside down triangles are empty. See if I have a nice picture of that. There's one in your textbook. I guess there's not. You know what it was? It was in 7.1. That's where the really nice picture of it was. Okay, so again, we're looking at a figure that has a sense of self-similarity to it. So imagine this taking out the center with an upside down triangle going on and on and on forever. What is the largest portion that's self-similar to the whole thing? You think of that piece. I think you have to do that for your for a Wiley plus. Which one? So we're looking for self-similarity here, and I was asking you for the biggest portion that's self-similar to the whole thing. And I would say this piece, right? This is the biggest part that's self-similar to the whole thing, or one of the other, there's 3 shapes like that. When you're doing your Wiley plus homework, this is half as wide as the whole thing, okay? So it's not looking at an area or volume, it's looking at width. If you took a ruler out and measured. So I have 12 centimeters for the whole width, and one of these triangles is 6 centimeters. Okay, so it's half as wide. But you could take smaller portions. I mean, you should all be able to circle a piece that's self-similar to the whole thing. So I could take this piece, or I could take this piece, or I could take this piece, or a little tiny piece right here. Okay. Oh, 7.1 Mindscape 2. Okay, so half as wide as the whole thing. Thank you. Now, Mother's Day will be next month, and you might want to make a fractal of yourself for your mom. Here's what the authors did. Okay, so the authors made a picture of themselves, and then they shrunk it down half as big, and they placed it in exactly this pattern, and then they repeated the process. So now they're going to take this big picture and shrink it down half as big and make 3 copies. And the 3 copies of this whole big thing will be placed in exactly the same area. So it looks like that. And they could keep doing that forever. Now if you do this too much, your mom won't be able to see your little face, okay? So don't do it too much. But fractals don't have to be all shrunk the same size. You can do more randomization, and that gives you other interesting looks. So here's, again, the authors taking their picture, but this time they don't shrink it down half as big. They make one, from the original 5-inch square, they make one 2-inch square, 1-inch square, and 1.5-inch square, and then they lay those in a different pattern. So the way you get interesting fractals is to make different patterns. So this time they are not evenly spaced out. They put the bigger one kind of in the middle, and then the little one staying square, and the medium one bottom right. Then they'll shrink that down again. Okay, same proportions though. You keep the same process. So we take a simple process and we repeat it over and over again. We do another iteration. So they shrink down to the same proportions they did to make this picture originally, and then they'll place it in the same positions again. And so see how it looks. You take, this was the one before, and now it's shrunk down there. And you can keep doing that again and again. So here's another iteration of that. So depending on the effect you get looking for, you get different ways of laying these out. Now you can really get some interesting proportions. Here we have a fractal that leads to what's called the Barnsley fern, a kind of famous fractal. So the original, it looks like a twig, and then the first copy is slightly smaller. The other two copies are much smaller, and the fourth copy is just a piece of the original, a little twig itself. Then those are all put together in a particular angle. So this is the angle that we see. There's the little twig and the two smallest copies and the medium copy. And here's a bunch of iterations. And if you do that enough, you get the Barnsley twig. Now there's a number of Barnsley, you get the Barnsley fern. There's a number of Barnsley fern generators online, so I have one here to show you. So this is a Barnsley fern generator. See, we're not doing the math behind a lot of this, but here's some of the math. This is done in linear algebra. You have to take calculus to get to linear algebra, but you can do linear algebra at some level without calculus. Anyway, these are done with points instead of with those straight lines. And depending on how many iterations you do, you get a different look. So if I just have 100 iterations, I'm not going to have much. Can you see those points even? Not too well, huh? But if I do 99, that's a lot. 999,999. Did I hit enter? Enter. There, that's quite dark. So you can see it grow if you like to by putting intermittent amounts in there. There's 20,000. So just by taking it, shrinking it down, and putting it where each of those points is. Take it, shrink it down, put it where each of those points is, then you get this look. It turns out you do not even have to start with a point. You see how the line that was in the picture and the points didn't make a difference? Well, you could even start with another shape like a car, or we could have used the author's face. And you get the same look. It's just because of the way you keep shrinking down, shrinking down, shrinking down, you still get the same appearance at the end. So in your textbook, you have some that I wanted to show you. Let's see if I have it here. There we go. Okay, so we have the Sierpinski triangle that we did with triangles, and we built up by stacking triangles. Here your author's stacking squares. Here he's stacking circles. Here he's stacking strange curve. Here he's stacking Sierpinski triangles themselves. and watch them grow as we shrink them down like we did, okay? So now these three will get shrunk down and placed one in each of those spots. Okay, these three get shrunk down and this picture gets placed in each of those three spots, and you see that happening. Then we shrink this down and place it in each of these three spots. And you see that happening. Shrink this down and place it in each of the three spots, and you see that happening. So your different pictures to start with, and then when you get to the end, they all look surprisingly alike because, again, of the shrinking down process. Well, I have a app that I thought I would show you because it's a lot of fun. If you have an Android, you can use this app. If you don't have an Android, we'll be looking at another app on Monday that's on the Apple, okay? But if you have your phone with you, we're going to look at this, okay? So this app uses the link system, and you can make your own fractals. So what it is on this system, you have a F for forward, and that will draw a line going in whatever direction you're aimed at right then. And then you can do a plus to turn, and you'll be able to tell it how much to turn. And then you can do a minus to turn the other way. And that's all you need. Now you can get more complicated, and we'll see some more complicated results from that, but this is all you need. So this is a free app, so if you have your phone, well, let's just try. Okay, before we do that, let's start with our initial stage of the Koch curve. Okay, so the Koch curve, you go up like this, then you go to the right, then you go to the left, and then you go up. So this would be a forward, and this would be a plus to make the turn. And then we go forward again. And now I want to turn the other way, right? So I'm going to go minus to turn the other way. But I have to turn the other way twice. Because otherwise, if I just turn the other way once, I'll be going straight again, and I want to go over more. Okay? And then I go forward. And then I want to turn again to the right. So I'll put a plus and then forward. So this would all be described with F plus F minus minus F plus F. That's how we could describe that. So we're going to get this downloaded, and then you can give it a try. Okay, this is OutSystems Studio. So let me show you what the app looks like. It looks like this little thing right there. So you can go to it's on Google Play, and it's at, what do I use here? I think I do use the Play Store. Okay, and it is a free app. Okay, I'll wait till you get it downloaded. Okay, this was not for me, okay? That was my daughter-in-law, okay? Unfortunately, this is for me. It's a good one, okay. All right, OutSystems Studio. No, I don't want that. I'm good. So while people are downloading, we can look at some samples. So I think this is kind of nice, this fractal plant. It's a little more complicated than the one we're doing, though. So when you hit this sign, it starts the iteration. So here's your initial one, and then we can add iterations. So it's going to take each one of these pieces and replace it with itself. and then another plus, and it'll do another iteration, and another plus, and another iteration, another plus, it does another iteration. And you can keep going like that. But we'll go ahead and make one. Anybody have any problems? How many of you got that downloaded? Anybody? Okay, yeah, it was okay. All right. So this time hit new. That's, I don't want any of that. Why does it have that yet? New. Okay, new. All right, so hit new, and the axiom is what we just figured out down on the paper down here. Okay, so we hit F, and then your plus sign, and then F for forward, and then your minus signs, and then an F again, and then a plus sign, and then an F. So that's what we wrote down. So we're going to go forward, right turn, forward, left, left, forward, plus forward. Now it needs to know how much you're turning when you turn, so I'll put 60 degrees right here. And then you can check it. Okay, so you can check it and see what it looks like. And see, there's our first iteration of our Koch curve. Okay, so forward, plus for right, forward, go left twice, so you're not still going straight after one left. Left, left, forward, plus for right, forward. Okay, now if I hit plus, now nothing's going to happen because I didn't do anything to tell it to replace. So use your back button. And now the rules come in, and you're going to tell it. You're going to tell it to take F, each of the F's, that's your starting thing that you had, and replace it with this. So I'm going to copy it all and take each F, so each line segment, and replace it with the initial copy. Just like we were doing on paper, only way easier because it's not on paper. We hit there, did it once already. Here's our second stage, third, fourth. So I think this is a fun app. You can fool around with different angles, different F's and minuses, looking at it, and really you can spend a long time on here, okay, and just have a good time making fractals. We'll see you again on Monday, and we'll look at Apple system there for all of you Apple people.